Hello and welcome to this video. My name is Aniruddha. Call sign is Victor Uniform 3 Foxtrot Mike Lima. I was going through this article on arrl.org website. It is titled "Do You Need an Antenna Tuner?" It is written by Steve Ford, Whiskey Bravo 8, India Mike Yankee. This article basically talks about the role of the antenna tuner. Here, if you see the first figure, it says that most transceivers are designed to expect an antenna system impedance of 50 ohms. When the antenna impedance is something other than the 50 ohms, a transmission line mismatch occurs and a portion of the RF power is reflected back to the radio. Standing waves are created in the feed line and high RF voltages can develop. When the standing wave ratio becomes higher than 3 is to 1, your transceiver may be at risk of getting damaged. So here we see the transceiver giving out forward power to the antenna. The antenna is not resonant at the frequencies that we want to use, and so it will show an impedance which is other than 50 ohms for which the transceiver is designed. As a result of which, part of the forward power will be reflected back, and that's how a high SWR is shown by the antenna. Now, if this SWR, according to the article, increases beyond 3 is to 1, it may damage your transceiver. The second figure shows an introduction of antenna tuner in the circuit. Now, the article says by using an antenna tuner, you can adjust the impedance your transceiver sees to a hospitable 50 ohms. The antenna mismatch to the line still exists, but the tuner protects your radio from RF voltages while allowing it to develop its maximum output. So here they have introduced an antenna tuner, and they say that you can adjust the antenna tuner such that the transceiver sees a matching impedance at as presented by the antenna tuner. And so since the impedance matching has taken place, there will not be any reflected power back to the transceiver from the antenna tuner. And so the SWR will be uh, seen as 1 is to 1 by the transceiver. It will be very happy and it will be safe. However, what is happening on the other side? The antenna is still not resonant at the frequencies that we want to use it for, and so there will be a mismatch present. Hence, part of the forward power, which is given by the tuner to the antenna, will still be reflected back, and there will be still a higher SWR presented by the antenna. This reflected power will be taken care by the antenna tuner, and the antenna tuner will be designed uh, to take care of the high voltages that might be developed because of the standing waves. It is a very nice article, and I will leave a link in the description below for the website. So, keeping this in mind, knowing what an antenna tuner can really do, I decided to make a simple antenna tuner. So, I've homebrewed an antenna tuner, more specifically LC match or LC antenna coupler. It consists of an inductor, a variable inductor that is, and a variable capacitor. And we'll look into the circuit diagram how it has been made. So stay tuned. So let us see what a LC match circuit consists of and what all things I've considered while designing the circuit. And to show that, I will just open the mmana-gal software, and let me just quickly open one of the antennas that I had drawn in this software. Let's open a dipole for 40 meters, and we will go to calculate, and for 7.1 megahertz uh, at a height of 10 meters, let's just press start. Here we see that the SWR is 1.61, and the impedance that is being presented by the antenna is 80.65 plus J 0.06. If we go to the HF components and to the LC match, the software suggests to use this LC match in order to match the transceiver side and the antenna side. If you observe here, the LC match consists of an inductor and a capacitor. Another thing to observe is that the impedance of the antenna is higher than that of the transceiver. Another thing to observe is that the capacitor is on the higher impedance side of the inductor. So here antenna is presenting 80.65 and the transceiver is 50. Since the antenna side impedance is greater than that of transceiver, the capacitor is on the antenna side of the inductor. Just to check, let us open another antenna. We will open 40 meter vertical antenna this time, and for the same frequency we will press start. Here the SWR for the vertical antenna is 1.36. If you observe here, the impedance presented by the antenna is 36.89 plus J 0.21. Let us go to the HF components and LC match. Here it can be seen that the antenna side impedance is lower than that of the transceiver side. The capacitor will always be on the higher impedance side of the inductor. Since the transceiver is having a higher impedance out of the two, the capacitor is on the transceiver side. So while designing the circuit for the LC match, we have to take care of this, and we have to provide a facility of changing the side of the capacitor, as we have seen in the horizontal dipole and a vertical antenna. We can provide a three-way switch by which the capacitor can be either connected to the transceiver side, or it can be connected on the antenna side of the inductor. We have to take care of this feature while designing the circuit. Another thing that we need to take care is we should provide a facility by which the inductor can be completely bypassed from the circuit. We should also provide a facility of bypassing the capacitor from the circuit. This way, we can make the circuit a little more flexible. Of course, as you have seen during the horizontal dipole and during this vertical antenna, the values of inductor and capacitor were different. And so, obviously, we should introduce a variable inductor and a variable capacitor to adjust these values. So let's see the circuit diagram of the LC match or the LC coupler that I have designed. This is the circuit diagram that I have considered in making the LC match or LC coupler. Here we see a variable inductor. This is the variable capacitor. The value of the variable capacitor ranges between 0 to 440 picofarad. We'll talk about the value of the inductor a little bit later. And as I said earlier, we have provided an arrangement, a switch to put the capacitor on antenna side of the inductor or the transceiver side of the inductor. You also see here a bypass switch which can bypass the inductor out of circuit. The inductor is in series with the center pin of the antenna connector and the transceiver connector, and the outer casing, that is the shield, is considered as ground. The other side of the capacitor is also connected to the same ground. So this is a simple LC match that we saw in the software as well. Now coming back to the value of the inductor, the software helps us in that as well. If we go to the HF components and to the coil, here we can fill in the details and it can give us the value of the inductor. So for example, let us do the computation for the value of inductor. Now I know that I've made a number of turns as 18. The diameter of the coil is 7.62, which is 3 inches, 7.62 centimeter, which is 3 inches. The diameter of the wire is 1.27 millimeter. It is a 16 gauge wire. So the diameter of the wire will be 1.27 millimeter, and the distance between the turns is 5 mm. So it shows us the length of the coil is 11.29 centimeters, and here on the top it has shown the value of the complete inductor. Of course, we'll be having taps out of the inductor coil, which will be given to a selector switch so that we can go on changing the inductor. So if you change the number of turns to 1, it will give the value of the inductor for the first setting. And similarly, if you go ahead, you can see the value of the inductor being changed. So this way you can know um, how to design the inductor. In my case, I had not kept in my mind what value of inductor I require. I wanted it close to 10 microhenry, and I achieved 12.5 microhenry. But you can design it perfectly using this tool. So let us go ahead and see the actual LC match that I have designed. I have kept the top of the box open so that we can see. If you see here in the front, these are the two switches. This one is the bypass switch, and this is the switch to switch the capacitor from one side of the inductor to the other. So here, this is the transceiver side, and this is the antenna side. So if I switch it to the left, it means that the capacitor is connected to the antenna side. And if I switch it to the right, it means that the capacitor is connected to the transceiver side of the inductor. This is the selector switch for the inductor. So it can go in up to 12 steps, and it changes the taps on the inductor. And this one is the variable capacitor. This is the transceiver side SO239, and this over here is the antenna side SO239. I've provided two wing nuts over here. One of them is at the ground, and this one is nothing but the center pin of the SO239. So I can connect a random wire or end-fed half wave and here, and I can connect a counterpoise or radials here. I've kept this to experiment with this antenna tuner for a random lens or end-fed half wave to see if they can perform well using this antenna tuner. So this is how I've made the enclosure is uh, wooden. I had some wood with me, so I just made it using wood and have painted it. But you can make it using different material as well. From the top, if you see, this is the inductor. Let me just change the camera again so that it will be clearly visible. I hope you can see it. So the variable inductor is of 18 turns, and I have tapped it at certain points, which is given to the selector switch, which you see here. And I can change the taps using the selector switch. This is the variable capacitor. I have used it from some old material, and so the value of capacitor was limited to whatever I had in my hand. So this is 0 to 440 picofarad, and these two are the switches that you see. So it's a simple design, really, nothing special in it, and it is easy to make. So let's see this antenna tuner or LC match, LC coupler in action. Uh, so I've connected the NanoVNA to the transceiver end of the coupler, and I've connected my fan dipole of 40 meter and 20 meter to the antenna end of the coupler. I've also connected the NanoVNA to the laptop using USB cable, and we'll be looking into the NanoVNA saver software. I have also bypassed the inductor and the capacitor right now. So uh, let's look into the NanoVNA saver software for the SWR curve. Now here, the antenna is resonant at center frequency, and the SWR is 1.4 at the center frequency. Now, whatever changes we are going to do to the coupler, uh, the transceiver is going to see those changes. The actual characteristic of the antenna is not going to change. Whatever changes we make and whatever changes are seen in the SWR and the impedance and the SWR curve in general, it's the transceiver that's seeing these changes. The actual characteristic of the antenna are not changing, as we saw in the article earlier. So the impedance right now at the center frequency is 55, which is greater than 50, so that of the transceiver. So which means that we have to shift the capacitor to the antenna side, and let's just do that as a step one, and let's observe the SWR curve. There is not much change in the SWR curve. The SWR as seen by the transceiver has changed from 1.4 to 1.3. It is still showing that it is resonant at 7.1 megahertz. So let us just change the capacitor a little bit and see what changes takes place. So the SWR is going down the value, and right now, okay. So if I take one of the markers to the lowest point, we are looking for the blue marker. Here you can see that the SWR is 1 is to 1 at 7.18 megahertz. So the SWR has gone down, but the resonant point, as seen by the transceiver, has also shifted. Let's say that we want a good SWR as seen by the transceiver, but we want the resonant point to be at 7.1. Now we want to take the resonant frequency from a higher value to lower value, which means that we need to electrically add certain length, and that could be done using the inductor. So let's just bring the inductor into the circuit and see what happens. As soon as we switched on the inductor, you see that the resonant point shifted a little bit down in the frequency. So right now it has shifted from 7.18 to 7.14. The SWR is 1 is to 1 as seen by the transceiver. Now let me just add a little bit of inductor further so that the resonant point shifts down the frequency. Okay, so it went past 7.1 and below it. So right now it the SWR, the resonant point is at 7.08. It's close to 7.1. Let's at this point let's just change the capacitor a little bit and see if we can make any difference. Okay, a little bit lower, a little bit lower. Okay, so if you see the green marker now, the SWR as seen by the transceiver is 1 is to 1, and the center frequency, which was 7.1. So the resonant point has shifted to 7.1, and the SWR is 1 is to 1. So that's how we can make changes to the tuner, and these are the changes that the transceiver sees. Again, I would say that the characteristics of the antenna have not changed. This is what the transceiver is seeing and believing. So this is how a tuner can be used in our operation, and yeah, it is very easy to make, and everyone should try it. um, I hope you liked this video. If you have liked it, please give it a thumbs up. Please also consider subscribing to my channel. It gives me great motivation to make such videos. And I'm very thankful to you for watching this video. Thank you and have a nice day.